Welcome to Everything Distributed. Today we are going to talk about replication, still in the case for distributed storage and replicated storage, but it's a different kind of replication called leaderless replication. And some of the content is based on chapter 5 of Martin's book and also from the Peter Bailis paper. It's actually the best paper of BLDB. I strongly encourage you to read it. It's a very nice paper. Just a recap, why do we want to use distributed database? Some of the key advantages are lower latency, higher scalability, and higher availability. And the key challenge is that we want to coordinate different machines. Once you have more servers and more clients, actually it's very difficult to coordinate them. And then last time we talked about that intuitively, we want the databases, all the machines to behave as a single computation or storage entity. Then the first part of this one today is that we want to formally define that. What do we mean? What exactly is the correctness condition that we want to achieve? And as a reminder, we simplify our life. We focus only on the key value pair, and our API, there are only two of them for support read operation and write operations. So we start with the correctness condition. It's called consistency. If you check the dictionary, actually I just checked Merriam-Webster today. What is the definition of consistency? There are tons of different definitions. One of them is that you want to find agreement and harmony, or like you want to investigate or ensure something between one thing and another. In other words, you want to have some inherent connection. And then that's why we like this notion in like lots of different things in distributed computing. So more formally is that when we set a consistency property for distributed storage, distributed shared memory, or replicated storage or replicated database, what we really means is that it's a set of conditions such that it specifies the correctness condition on the relationship or the connection between different data items, and usually not only the data items, we also care about the results of the operations. Okay, so two things to remember, it's a correctness condition, and it's usually we want to argue that what is the correct data items to have in the systems, or what is the expected outcome, expected result if as a client issue a certain operation. Okay, so that's the big idea of the intuition for the consistency. Then there are tons of consistency guarantees or consistency properties, and I think the most popular one are usually the client-centric views. So you don't really argue what are the data items that I store inside the storage. Instead, you don't really care about what server observe. What you care about is that what client would observe. Okay. And then there are tons of consistency ranging from the strongest one to the weakest one. And usually the strongest one is called strong consistency, but it's a kind of catch-all name. Later on, we will see that many different versions of a strong consistency. And then of course, on the other end of the spectrum, there are also tons of different kind of eventual consistency. So eventual consistency is like a catch-all term. And today we only focus on the three things in the middle. It's read your write consistency, sometimes also called read my write or read after write, and monotonic reads and consistent prefix read. And you might say that why all these three are related to read operations? Because in nowadays workload, most of the database or most of the application actually is read intensive. So think about Instagram or Facebook, so that it's not likely that you are going to post tons of things a day, right? But like when you use Facebook, when you use Instagram, most of the time you are absorbing information. You are reading others' posts, reading others' picture, video. So there are tons of read. And that's why like in many of at least for the social network application, this consistency aspect for reads are very important. And then once we define certain type of consistency, there are all kinds of trade-off, like in terms of how you design a system, how you implement it, how do you operate in your system. So for example, you might have a consistency latency trade-off, and then the most famous like CAP theorem, we have a consistency, availability, and partition tolerance. And then we also have a consistency, like different kind of fault tolerance, and all kind of trade-off, and later on we will see some of them. And then the general rule, the rule of thumb to remember is that for consistency, is that usually you can define something like lattice. Lattice is that you have a one strongest one and then one weakest one and then many things in the middle. But like what we mean by stronger is that if something satisfies this consistency A, it must satisfy the other thing called consistency B, then this implies A is stronger than B. Okay, and then in general, when we have a stronger consistency, that usually means that you need to spend more times to do coordination, and then that will make your system slower. But on the other hand, stronger consistency is very good for clients, for users, and for application developers that use the database, that use the shared storage, because it's very easy to write, it's easier to reason with. So the strongest one is that it gives you the illusion that you are always using only one machine, regardless of the partition, network failure, or that machine failure. So that's very good. But the downside is that performers, because of some like kind of inherent impossibility in distributed computing, it's impossible that it will get super good performance. And then in many of the application, you don't really need stronger consistency. So you can use weaker one. It usually has a much higher performance, but the downside is that it's very difficult to develop correct applications. Okay, now let's look at like three of the read-specific consistency. So read your write. If you have like some exposure to the database, that it should be very intuitive to guess what read your write means. What it means is simply that whenever you write some data, suppose that this person writes some data X, okay, and then this day say, okay, the leader said acknowledge that you got it. Then you will want that, okay, I'm going to read this thing again. Then this database should return X. So that's read your write. But suppose your read is unlucky, you go to the server that is slower, then it will return something, say that, okay, it's a null value, and this does not satisfy read your write, okay? So the first read is okay, but then the second read is not read your write, okay? And then now let's go to the next one. It's monotonic read. It's very similar to read your write consistency, but in this case, you don't really have the write. Okay, so you just with respect to a sequence of read. Suppose this client, and then suppose you already have a data that's called the key K, and then the value is X. So if you do a read, and then the system return X to you, and then you do another read, the system return X to you again, then you are happy. This satisfies monotonic reads. So intuitively, what it means is that whenever I read something, I must read a newer version. But I suppose in this case, you are unlucky, okay? Then the second server just return a null value again. then this is not monotonic read. Okay, so the first one is good, but then the second one is not good. It's not monotonic read. Okay, and now let's see the third one. It's called consistent prefix. For many of the applications, if you only argue with a specific or a single pair of a read or write operation, that is not enough, because you want all the clients to observe the same history. So now suppose that you are doing a synchronous replication for your database, and then somehow that the first server, it observed like X before Y. But like in the second server, it observed Y before X. And then this will cause some issue, right? So if like both client access the first server, then you are doing good. Everybody observe X before observing Y. But like in this case, if like 1 and 2, they have inconsistent view, they observe that the ordering of the value is different, then you will have a problem. Okay, so let's say client A, first it reads something, it say, okay, this is X. Then second, it reads something, then the system tell that, okay, it's a Y. Then for this client, it's a bit different. So it first read, and then it got it, okay, it's Y. And then it reads again, then it learns that, oh, okay, it's X. And then in this case, it does not satisfy consistent prefix. Okay. So that's the meaning of consistent prefix. Now let's go to the next one. So yeah, you should be able to think about that, okay, what's the benefit for each of the consistency? Because it really depends on your application. You need different kind of consistency. And one rule of thumb is that you want to use the weakest consistency that can satisfy your need, because that will give you the best performance. And then there are tons of solutions to provide or to guarantee those three consistency properties. There are very simple ones or very complex one, and it really depends on like what scenario you have in mind, like what kind of operation you need to support, what is the hardware, or are you doing this within a single data center or multiple data center, or even like geo replication. Then what are some of the data, what's the workload, and what kind of force are you expecting. There are tons of different options. And then usually the way we want to figure out that which operation comes first, or that we want to figure out that which version that we want to show, we need to have some forms of clock or some types of clock. So last time we talked about this kind of synchronous clock. Later on we will talk about logical clock, physical clock, and then we will also talk about causal clock. Those are necessary in order to solve this problem efficiently. Okay. Now let's go to the second part of the today, which is on leaderless replication and quorum replication. And then for this one, it's very different from the leader-based replication, because that basically each server, they are equal with each other. They have the same responsibility. So right now we assume that all three servers will have the same piece of data items. Okay. Then usually for Quorum storage, it goes as a client. It will contact randomly with some server, some machine, and then this server will serve as a coordinator for the client. Okay. Then basically this coordinator will contact others, say that, hey, this person wants to do a read or want to do a write operation, and then they will return then back to this coordinator, and then the coordinator will reply to the client. So this is the entire flow of the system. Then why do we want to do quorum storage? structured. So now if you remember from last time, if we have follower failure or if we have leader failure, then that will cause some disruption of your system. But like in this case, it's that even if like some of the machine fails, then you can still operate it in a sense. Of course, if like this client, this coordinator fail, it's a little bit trickier. But like even in this case, the client can use timeout mechanism, say, oh, yeah, this coordinator is not responding. I should contact a new one instead. And then this is like pretty easy to achieve. Okay. Then now let's look at that more detail, like how do we exactly to do that the read and write operation. So there are two parameters that you want to remember. The first one is like W. It specifies the size of a write quorum. So what's the size of write quorum? Here's an example. The client tells the client coordinator, hey, I'm going to write something. And then this coordinator will forward the write to all the replicas or all the other servers, and then it will wait until it collect another acknowledgement, and then you can reply the client said, okay, now your write is done. So in this case, oh, okay, sorry, actually here I miss it. What I said here is actually W equal to 2, because that how many acknowledgement that you already receive? You receive acknowledgement from this guy and then acknowledgement from this guy. So that gives you like 2 egg for a single write operation. And then if you like W is equal to 1, actually that you don't really need to wait this acknowledgement. You can directly reply to the client before hearing any of the acknowledgement from like these two servers. Okay. Now let's look at the read. So for the read is similar. Here you specify the number of read quorum. So here the intuition for the quorum is that the number of servers or the number of machines that have replied the coordinator. So in this case, okay, the client again said that, hey, I'm going to read something, coordinator for something to the other servers, and then our server will reply with some value, and then this coordinator, it will need to check. Because locally, it also has some version of data, right? Suppose it's V prime, then it will need to check that I receive a V from other server, and now I will need to see that whether V prime is newer or V is newer. And I always try to return the newer version back to the client. So suppose that V prime is a newer version, it will return that. Okay. And then here, how do we distinguish it with like newer version? Then we can use all kinds of clock. And then here we just assume that we use machine times, because suppose it's within a single data center, then everything at the clock is very well synchronized. Okay. So the key thing to remember is that this workflow, and then the notion for coordinator, and then also all this parameter, I mean N equal to 3, F equal to 1, W and R. Okay, so F is that the upper bound on the number of faulty servers that you want to be able to tolerate. Okay, and now we go to the next slide, is that remember what's the correctness condition? We have liveness and then we have safety. So in this case, liveness, what does that mean? And then for safety, simply that we want to achieve certain consistency. And suppose here, we want to achieve strong consistency. And then here, the intuition for strong consistency is that suppose a write is complete, then any newer read must return that write, or an inversion newer. Okay. So in this case, then what is the relationship between the N, F, and R, and W? so that we can guarantee that these two conditions are satisfied. So what's liveness? It simply means that I can contact enough number of quorums, meaning that you need to have enough machines that's alive to satisfy your request. So if you remember, how many remaining nodes are in the system is n minus f. So, okay, so here's a typo. This should be like n w greater than or equal to n minus f and r greater than or n minus f, because that you have n minus f nodes remaining in the system, and then you want to get not many of the replies. So this two inequality are already enough. And then strong consistency is that r plus w has to be strictly greater than n. The intuition to see this is that suppose this is a right quorum, and then w equal to 2, and what that means is that once the right complete both of the right quorum will have this version of data b. Then later on, once you have another read comes in, so you have r equal to 2. Then remember, how does that coordinator figure out which version of the data to return? It will guarantee to read the previous write. Okay. So in this case, you are guaranteed to return the value for the most recent write. And then that's already sufficient to satisfy at least one version of the strong consistency. Okay, and then one thing for you is that to think about the exercise is that why is that this condition r plus w greater than n is enough to ensure that there's a intersection between two quorums. And then a hint is that this is something very similar to what we discussed last time. Okay, let me clean up the drawing. And then in practice, you might say that what is right quorum size? And then that really depends on your guarantees. What's durability? What's your consistency? What's your latency tolerance? And then remember the first type, the article I mentioned by Peter Bailis. They investigate that in industry, what are reasonable choice. And then they figure out that actually that, for example, Amazon or LinkedIn, they adopt this a partial quorum notion, meaning that it's not r plus w strictly greater than n. Usually r and w is very small and n is greater than or equal to the sum of those two. And then in this case, they analyze that what would be the consistency and latency trade-off. And one big idea, the intuition, is that the longer you wait before you issue a read operation, then the more consistency you will have. Then what is this consistency? They introduce a notion for this probabilistic bounded staleness. Okay, meaning that how much time you need in order to read how much time that you need to wait until you can read the newer version or read the most recent version. And they provide all the analysis, and then they also provide a simulation, and then they also implement their evaluation and monitoring framework into the system. It's a very nice paper. Okay, so that's all for today. The 3 takeaways. We discussed this and the notion of consistency. Why do we need them? And then what are the 3 key consistency regarding the read operations? And we also briefly discussed this notion of a leaderless and quorum replication. And finally, in the final slide, I talk about the partial quorum. All right, that's all. Thank you.